So, dear colleagues, welcome to the this lecture series number 18 on Azadi ka Amrit Mahotsav that our institute organizes. And we have a very distinguished speaker today on a very exclusive topic, should I say, which is application of isotope in hydrological investigations. And we are all professionals working in the field of conservation. And this is one technique which has potential to address, I think, all our problems of establishing impact assessment of conservation measures. So Dr. Sudhir Kumar is actively working in this field for the past 35 years. And when I requested him, this lecture was postponed 1 or 2 times. I requested him, he readily agreed, not because he is a very good friend of mine, because he likes to speak on this topic. Not many professionals in our country are there who work in this area and can speak on this coveted science, which is isotope technology. And Dr. Sudhir Kumar has not only mastered, it is not about the data collection and using the technique. It is also about the analyzing the data and making useful interpretations out of it. And Dr. Sudhir Kumar has applied this technique in solving many real world problems in hydrology. So we'll listen to him. We are very fortunate to have you, Dr. Sudhir Kumar, with us among all our colleagues from far-flung, from all over the India. And I'll just also inform the audience that not only works on solving practical problems using this technique, but he has also established a very well-developed lab in NIH for applying in this particular technique. And that lab is very best in India, in our country. So also gracing the occasion is our director, Dr. M. Madhu, with us this webinar, and our head of the divisions, Dr. Khola, our friends who worked on isotope technology, Maurya, Dr. Goel from Kajri, and many others. You can see the participant list. From every corner of India, our friends are there who are interested in this topic. And we have our coordinators, Engineer Srimali and Sridhar Patra, who will be now taking over and conduct the webinar. So Srimali ji, please go ahead.
Thank you, Dr. Ojasvi, for an introductory remark regarding today's webinar in the series of Azadi ka Amrit Mahotsav. I welcome Dr. Sudhir Kumar for this occasion. Also, in the present seminar, present our director, Dr. Madhu, our senior colleagues, Dr. Khola, and others joining from different ICR institutions. I will just briefly introduce today's speaker. Dr. Sudhir Kumar is presently based with the National Institute of Hydrology based at Roorkee. He is a PhD in Earth Science from IIT Roorkee, and he specializes in quaternary geology, geohydrology, and geomorphology. He started his career with NIH Roorkee in April 1987 and continued with NIH in various capacity, and presently he is heading the Hydrological Investigation Division, and he is a scientist SG He worked on various areas, isotope analysis of spring discharge in far western region of Nepal, integration of isotope hydrology in aquifer mapping, groundwater management, surface water management, and interaction at selected location, assessment of groundwater resources and development of potential of Yamuna floodplain and city Delhi. His research areas are isotope hydrology, groundwater management and modeling, hydrological investigation, hydrology of mines, coastal area, hard rock areas, and spring hydrology. This is one of the topic which all of our institution who are based in hard rock areas where you want to trace the movement of the groundwater will be of use to them. And I now request Dr. Sudhir Kumar to take over the floor and give his talk for today. Thank you.
Thank you, Dr. Rajeshri and Dr. Mali, for the kind words. I am a simple and a grassroots worker, you can say. I do not need that much of introduction, but still I will like to talk on this topic, and now it has become my favorite topic, and hope I will do the justice with the topic and will try to convey some of the things, some of the techniques which we use, and some of the case studies which we have done working at NIH. So can I share my screen now? Yeah, can you see my screen? Can you see my screen, please?
Not yet.
Not yet, sir.
Not yet.
Okay, let me again check it.
It's a request to the audience, please mute yourself, except the speaker.
Now?
Yes. Yes, sir, it is visible now.
Okay. So thank you very much for inviting me for this lecture on application of isotopes in hydrological investigations. So as I have been introduced, I'm working at National Institute of Hydrology, Roorkee for last 34 years now, and I am into this field for last 20 years. And we have a very good laboratory, and I am proud of our laboratory. We participate in inter-laboratory comparison worldwide, which is conducted by International Atomic Energy Agency. And normally our results, what we get from our laboratory, are of the top ranking. So we are very happy to tell you that our laboratory is fully functional and is being used by many people in the country, and now even from abroad also we are getting some request for analyzing the samples. So with these words, I will now try to tell you about this technique and how we use it, because you are all engineers and very well versed with many of the things, but still maybe for some people it may be a repetition, but I have to, I think, tell all about all
sir,
of it.
Sorry to interrupt. You can put it on presentation mode, sir.
Presentation mode. Okay.
Yeah.
Sorry. Okay. Now is it visible? Okay. Now is it okay?
Yes.
So let
Yes,
us start with the basic definition of hydrology. So it is the study of distribution and movement of water both on and below the Earth's surface. So we are dealing in this with atmospheric water, surface water, groundwater, and everything, and as well as its impact on human activities. So even ecology also comes under some part of ecology is also related to hydrology. So when I talk about the atmospheric water, so we study the effect of temperature due to global warming on snow and glacier melt, rainwater chemistry and its effect on surface water and groundwater quality, study of long-term effects of climate change on various components of hydrological cycle, Then we in surface water, we are interested in integrated basin planning, development and management, development of methodology for fine tuning the present procedure for the surface water resources assessment at basin and sub-basin level, snow and glacial melt modeling, comprehensive hydrological study for mix and large tanks. Then in groundwater, we are interested in the improvement of methodology for assessment of yearly renewable groundwater in all zones, development of cost-effective technologies for artificial recharge, regional groundwater studies, identification of hydrochemical processes, monitoring and modeling of hazardous chemicals in groundwater. Then in the estuary and deltaic area or the coastal areas, we are interested in demand management for preventing saline water ingress in deltas and estuaries, protection of water quality in estuary and deltaic areas, freshwater saline water interrelationship in coastal areas, hydrological impact analysis due to tides and cyclones. Then we have many other hydrological issues, estimation of irrigation return flow, hydrological mapping of hydrological variables, integrated watershed management, contribution of storms to water availability, erosion, sediment investigations. So many of these issues and our issues in surface water, groundwater, water quality, and all other irrigation related issues, we have the application of isotope hydrology. So isotope hydrology facilitates the systematic measurement and interpretation of hydrological information that may not be obtained easily by any other means. So it is a technique, we can say, so many things which we cannot do with other techniques. Let me tell you one thing. When we talk about water as per chemistry is H2O only, but as we see it in terms of isotopes, we have 18 types of water. I will come to that. So then many things which we cannot do with the other methods or traditional methods that can be done by this technology. Isotopes offer a set of unique tools which are often the cost effective and easiest to use. Many people may contest this statement, but still I will tell you only the cost of equipment is high, but the analysis cost is very low. So we are, the use of equipment is not very sophisticated. Any trained technician can use can use the instruments for analysis in the laboratories. Isotopic information is usually combined with other hydrological information to produce a comprehensive understanding of a hydrological system and provide a scientific sound basis for management decisions. This is, I will say, the only shortcoming, maybe you can say shortcoming of this technology, that alone we cannot use the isotopic data for interpretation. We always need the secondary information about the processes or the area to have a very sound conclusions about the processes happening in that area. So the isotope hydrology, basically the modern isotopic hydrology, is based on the discovery of isotopes, which was done sometimes in 1920s and 30s, which was followed by determination of natural abundance of carbon-14 and tritium in 1946, and then research continued on this, and the applied aspects of isotopes in hydrological research, that is isotope hydrology, is relatively a young scientific discipline that started around the 1950s, when it was first realized that isotopes can play an important role in developing a better understanding of hydrological processes. So it is only science which has been developed in last 60 to 70 years, and though some concepts of this technique are taught in chemistry and physics in undergraduate level also, but its application are only a subject matter of higher education. Now, there are many questions which we can answer using this technology. What is the origin or main source of water, from where the water has come? If I am looking at water in Ganga plain, in the 4th aquifer or 5th aquifer, where is its recharge zone? Is there any present replenishment of groundwater in the aquifer, and if yes, how much? From where it is, whether the water is connate water, that is old water which is not linked with any recharge area. So, and how much water is available, that this type of answers can be given by this technology. What will be the consequences of intensive exploitation of groundwater in this area? If we are going to develop an area for from groundwater point of view, and are extracting a lot of groundwater, then what impacts it is going to happen? Is the groundwater recharging in mountains? Where is the recharge zones? Is there a risk of contaminating wells? Or does a decrease in water table endanger water supply? Is it salinization or saltwater intrusion in the coastal area? Whether, because many people have wrong this notion in India that coastal areas salinity is only due to saltwater intrusion, but it may be due to some other processes that can be clearly understood using isotopes. Are we using fossil groundwater? That means very, very old water. If we are using, that means if the groundwater is very, very old, then that means it is cut off from the present day recharge. So what is the consequences of using such waters? Are these water, are these two, so if we have a multi-aquifer system, then whether the aquifers are interconnected with each other or they are not, they are separate. So that this type of answers can be given by this technique. What is the interaction between surface water and groundwater bodies? Whether the surface water is feeding the groundwater or groundwater is feeding the surface water, that can be easily traced using isotopes. What is the groundwater velocity? With what velocity the groundwater is moving subsurface? How can we rejuvenate a dying spring? So we can find out the recharge areas in the spring shed, and then can try to create some artificial means for recharging that area so that we can rejuvenate the dying springs. How can we identify a pollution-free source of water? Will a large investment to be done on industrial or colonization is in an area be fruitful? Because it requires a lot of investment to develop areas, whether the water will be available in long run or will it be sustainable or not. These are the requirements which we need to answer, and isotopes are a very good tool for these are some questions which we have listed out. There are many more areas of application where this technique can be used. The power of isotopic tools, the body of water appears much like another. As I told you, water is H2O for chemist, physicist, and everybody. But for if you see it at an atomic scale, it can be identified by natural isotopic composition of its water. We can, I'll come to later on. During evaporation and condensation processes, the concentration of oxygen and hydrogen isotope in the water molecules undergoes small changes. The heavier isotope in water molecules evaporate more slowly and condenses more quickly. This makes water in different forms at different locations distinguishable. So this is a very important aspect of isotope hydrology. The fractionation which takes place is very important to understand the processes which are happening on water. So the environmental radioactive isotope provides unique information about the age of water, which tells about the dynamics of groundwater dynamics in an aquifer. So whenever there is a movement of moisture from one place to another, so the path it goes on recording the isotopic composition, and then we can understand what has happened on that source. So if there is a cloud, this is ultimately nothing but a hydrological cycle. There is cloud, and then there is a rain out processes, rain out or snow process. Due to condensation, there may be evaporation, and that is related. That depends on temperature and relative high humidity. Then some waters enter into the ground from the groundwater. Rest of the water may even get retained in the soil, or it moves to the rivers or lakes or water bodies or sea, as the case may be. So now let us start with some very basic thing, so that we can build up the story and can understand how this science works. So isotope is nothing but these are the atoms of an element which occupy the same place in the periodic table. So that means because the periodic table is based on the atomic number, so that means they have the same atomic number but different atomic weight. So That means they have the same number of electrons or protons, but different number of neutrons in their nuclei. So if I talk about the hydrogen isotope, because we are much more interested in water, so hydrogen has 3 isotopes: protium, deuterium, and tritium. So protium, when I talk, it is the single proton in the nuclei. Then we have deuterium. It's this weight is 2, and it has 1 proton and 1 neutron. And tritium has 2 neutron and 1 proton. So we have 3 hydrogen isotopes: protium, deuterium, and tritium. Similarly, for oxygen, we have a large number of isotopes. Around 8 we have isotopes, and the normal atom is O16 with 8 protons and 8 neutrons in the nuclei. Then we have O17, which is with 8 protons and 9 neutrons, O18, 8 protons with and 10 neutrons, and so on and so forth. So then we have, because I am just first giving some concepts, and then we will talk about the hydrological implications. Then we have, if we have the same number of protons, we call it in the nuclei, then we can call it as isotopes, that H1, H2, and H3. If you see vertically here, if we have the same number of neutrons, we call them as isobars. That is hydrogen, this is deuterium and helium-3. Then if diagonally, if you see, we have the same atomic weight but different elements, that is carbon-14 and neutron, nitrogen-14. So this atomic weight is the same, but the atomic number is different. So the isotopes, normally what we have various sources from which the isotopes are formed. They are formed in the atmosphere, or due to cosmogenic activities. And isotopes which are produced in the due to cosmogenic activities are tritium, that is H3, then carbon-14, silicon-32, chloride-36, argon-39, krypton-81, and iodine-129. Then some are produced subsurface, that is helium-4, then chloride-36, argon-39, krypton-81. Then due to decay of your decay of this uranium series, you can say radium, radon, thorium, uranium, etc., etc. And these are also produced in the due to the nuclear weapon testing, reactors, and fuel processing. These are tritium, carbon-14, chloride-16, 36, krypton 85, and iodine 129. So now as far as isotopes are concerned, we have 2 types of isotopes: stable isotopes and unstable isotopes. And a third category we call it as the environmental isotopes, because these are the isotopes which are present in the nature. So which are present in the environment, whether it is stable or unstable, that is radioactive, are called as the environmental isotopes. So stable isotopes, these isotopes do not decay with time. Most of the elements have stable isotopes. Many stable isotopes are available in the Earth's atmosphere. For most of the hydrological studies, environmentally occurring stable isotopes are used. Then we have the unstable isotopes. They are also known as the radioactive isotopes or radioisotopes. Then these isotopes decay spontaneously and emit radiations, which may be alpha, beta, or gamma radiation. In the process of decay, the atom transforms from one element to the another element, and this series continues till a stable isotope is formed. Then in case of radioactive isotopes, we use the concept of half-life. That is the time required to decay 1/2 of a given number of radionuclides into half, and it is denoted by T half. And this is used for groundwater dating. So this decay equation we use for dating, and in groundwater dating we use a number of radionuclides, but most commonly used radionuclides are tritium and carbon-14. Tritium is, I told you, H3, and it has a half-life of 12.32 years, while carbon-14 has a half-life of 5,730 years. So that means it takes 12.32 years to become 100 grams of tritium to become 50 grams. And then from 50 to 25, again 12.3. This is an average time. This is not fixed for each and every atom. but it is the average time taken by to reduce from 1 to half. Then these are some units. I don't think this is much of use. Then environmental isotopes or stable isotopes. I told you it may be stable or radioactive. So these are not harmful. So isotope hydrology people sometimes are afraid that you may have health hazards if you are working in isotope laboratory. But normally we are using only the environmental isotopes. That is the isotopes which are present in our environment. So we are not introducing anything into the system, so it may become harmful. So these isotopes, environmental isotopes, are available in the Earth's atmosphere. We neither have to buy these or not to inject anywhere. Naturally introduced in the hydrological cycle, different processes are responsible for variable concentration, that is evaporation, condensation, or mixing. Very sophisticated instruments are available to measure both radioactive as well as the stable isotopes. Now, I was talking about oxygen isotopes. So here we have listed 6 isotopes of oxygen. They are 14, 15, 16, 17, 18, and 19. The ones with red are radioactive. Now you see, oxygen 14 has a half-life of only 72 seconds. 15 has a half-life of 120 seconds, and 19 has a half-life of 29 seconds. Because the half-life is very, very small, so they are just produced and they decay. So it is not possible still to use these radioisotopes for any purpose in hydrology. So we use only the stable isotopes of oxygen, which are 16, 17, and 18, and their general abundance, if you see in the nature, is this 16 is 99. This is the most abundant isotope of oxygen in the nature. Then 17 is 0.037%, and 18 is 0.204%. Similarly, for hydrogen, I have already told you there are 3 isotopes. 2 are stable and 1 is radioactive. So stable isotope protium, this is 99.985%. Deuterium is 0.015%, tritium is 12.32, has a half-life of 12.32 years. Now tritium, when we are talking about, this is produced in the atmosphere by interaction of cosmic rays with nitrogen. You can see this equation. I am not going to elaborate this much. This neutron hits nitrogen, and tritium and normal carbon mass are formed. These are also produced due to testing and explosion of nuclear weapons, operation of nuclear reactors and particle accelerators. You may be aware that now this testing of nuclear weapons or nuclear on surface of the Earth is banned. In 1960s, due to this activity, when America and other countries tested these weapons, the concentration of tritium increased in the atmosphere, and which is normally in the range of 5 to 10 TU. 5 to 10 TU, when I talk about 10 TU, 1 TU is equal to 10 raised to power minus 10, 1 atom in 10 raised to power 18 atoms. So this quantity increased drastically in the atmosphere, and this tritium concentration in atmosphere had gone even up to 7,000 TU in certain parts of the world. So due to this increased radioactivity in the atmosphere, the use of this testing of nuclear weapons on open surface was banned in 1963, and all the nuclear testings now after 1963 are allowed on the subsurface or in the water. You can see here, this is one in the northern hemisphere. You can see how much the activity of tritium increased in the atmosphere during 1963, and it slowly died down, and now the natural production is between 1 to 15, or in India it is around 5 to 10. So I told you 1 TU, the unit in which the tritium is measured is 1 atom in 10 raised to power atom, or it is equal to 7.1 disintegrations per minute per liter of water. If in the water we measure the radioactivity and we measure it as disintegration per minute, if there are 7.1 disintegration, that is the activity is 1 T. So tritium is continuously being produced in the atmosphere. Then once it is produced in the atmosphere, it is incorporated into water molecules. The residence time in lower troposphere is 5 to 20 days. And once it is in water molecules, then it falls on the earth in the form of water, and then its life starts. And then similarly, carbon isotope. Carbon isotopes are used. This I told you the half-life is 5,730 years. In carbon, we have 16 known isotopes. Carbon, though not a direct part of water, but in most of the water we find carbonate bicarbonates. Okay, so it is a very, very useful isotope in terms of for hydrological studies. And we have from C8 to C23, the 16 isotopes present, and the C12 and C13 are stable. C14 is radioactive with half-life of 25,730 years. Other isotopes are also radioactive, but very small half-life, because to measure very small this half-life radioisotopes is difficult for hydrological processes. The C13 isotope is used as a proxy for nutrient cycling and the temperature-dependent air-sea exchange of CO2. In aqueous geochemistry, the source of surface and groundwater can be identified by analyzing C13 values. This is used in climate change and pollution studies very much, because it gives an idea about the source of carbon. Then this carbon-14 is also produced in the atmosphere by the interaction of neutron with the nitrogen. It depends on the velocity, or you can say energy in the neutron which hits the nitrogen, whether carbon will be carbon-14 will be formed, or normal carbon with tritium will be formed. So it depends on the energy which is there in the neutrons which is hitting the nitrogen atoms. Then this again, once carbon-14 is formed, this is just like a normal carbon atom. It incorporates into CO2 molecules and reacts with by reaction with oxygen, and then or by exchange with stable carbon. And this carbon-14 led CO2 mixes rapidly in the atmosphere and hydrospheres and attains constant levels of concentration. When a plant or animal dies, so or when water infiltrates into the ground, the continuity is broken and the carbon-14 decays according to a governing radioactive law. And we can miss as soon as it enters into the ground, it is cut off from the atmosphere, so its age starts. Similarly, for tritium, as soon as it enters into the ground, after infiltration, its age starts, and we measure after that how much decay has taken place to find out the age of water at a specific point. So, for dating of material, we have various radioisotopes which can be used for different ages, because all isotopes cannot be used for modern or short recent ages to find out the recent ages. But some of the isotopes which can be used even for finding out of the age of material, which may be up to 10 million of years or more than that. That is, we can use carbon-14, which are for the waters which are around 10,000 to I'll say 2,000 to around 40,000 of years. Tritium is used to find out the age of water recent, that is maybe you can say 2 years to maybe 30-35 years. So similarly, we have krypton, then carbon-14. I have told chlorine can be used. So there are different techniques, isotopic radioisotopes which can be used for finding out the age of the material from a few years to millions of years. Then when we work with the stable isotopes, we represent it in terms of per mil, that is per thousand. It is not per percent, it is per mil is per thousand, because the quantity, the variation is very small. It is expressed as per thousand. And this is the equation where we take the ratio of the heavier isotope to lighter isotopes in standard minus ratio of heavier to lighter in sample and standard, and this is the equation, and it is represented in delta notation. So because I am not going in very much detail, I will just give the concepts, and these are the some of the standards which are used. These are the standards which are given by IAEA. We have the VSMO, Vienna standard mean oceanic water, then SLAB standard. So we measure actually the isotopic variations with respect to a standard, and always represent with respect to a VSMO. That is the variation with respect to VSMO is represented basically, and we see how much the heavier isotopes have gone out of the water molecule, and then try to interpret it. So we have different standards because VSMO is basically nothing but a mixture of all the ocean water. We take its value as 0,0. And then we have GS SLAB. These are the other standards which are there for the measurement of the isotopes which are in very cold or in the middle type of your climates. So I will not go into this. Then we have one term isotopologs, because water, as I told you, the molecule of water is H2O, but isotopically you have 18 types of water, and these are known as isotopologs. It depends upon the number of atoms of hydrogen of these isotopes which are there, or oxygen isotope which is present there. So if you make the permutation and combinations, this gives rise to 18 types of water isotopically. So this is one type. You can say normal water is O18. H2O is 18, 1, 1, and 16, but you can have 1, 1, 18, 20, 19. So this type of this, you can have a different permutation combinations and have different molecular weight of the water molecule. But mostly 99.8% of the water has the normal water molecule, which is H1 and O16. Then there is a fractionation which takes place when there is a phase change, when the water, this liquid changes to vapor or vapor changes to liquid. This due to condensation, evaporation, or sublimation, there is a fractionation, and this isotope fractionation is a physical phenomena and depends on the difference in mass of various isotopes of an element and temperature at which the isotope fractionation takes place. Mainly, we have two types of fractionations. That is equilibrium fractionation, which takes place at the time of condensation, and kinetic fractionation, which takes place during the evaporation. So when there is a phase change, so some heavier molecules may go to from liquid, and in the reverse case, the heavier molecules will be retained in the water liquid phase, and lighter will evaporate. And this is alpha is nothing but the fractionation coefficient, and this is temperature dependent. And you can see as the temperature increases, the fractionation decreases, because at higher temperatures, all heavy and lighter molecules can evaporate from the water body. So there are different this fractionation is temperature dependent, but temperature and humidity dependent both. But this is a very important, this graph which you can see through cursor where they are using. So this is basically I'll come to this a little bit later. This is a very, very important evaporation line which has been shown on this, which is due to fractionation and can be used for understanding the hydrological processes. But when there is evapotranspiration, there is no fractionation, because it takes the same water which is there in the subsurface as soil moisture or as groundwater, and it goes through the trunk of through the roots, trunk, and the leaves, and then it is transpired into the atmosphere with the same this isotopic composition. So there is no fractionation when transpiration is there, but when there is evaporation, then there is a fractionation. Now this fractionation depends upon number of factors. These are continental effect, altitude effect, latitude effect, seasonal and number of effect, and sometimes we also add the paleoclimate change, though it is not a process which involves fractionation, but it can be used for certain understanding of some of the processes. Then, first is the continental effect. As the moisture moves from the ocean or in a water body or any source from where the moisture is generated away from the source, rain-out process takes place. And when rain-out process takes place, what happens? The heavier molecules, because they require more energy to stay in that vapor phase, they drop down. So as the moisture moves for a longer distance, its heavier component goes on decreasing. So moisture becomes lighter and lighter in isotopic composition. So we represent that decrease from standard in terms of this depletion. So that means how much heavier molecules have gone out of the vapor phase. So that is, if you move away from a moisture source, then you see this phenomena. So the rainfall taking place in the coastal area and rainfall which is taking place at Delhi or Dehradun have different isotopic composition, because the moisture which comes during the monsoon season is mostly from the Bay of Bengal or Arabian Sea. So then we have the altitude effect. This is also a very, very important aspect to understand, because when the moisture moves up slope, again, what happens? There is adiabatic cooling. Adiabatic cooling, when there is orographic effect, there is adiabatic cooling, and then again, when there is a cooling, the heavier molecules or the heavier atom, these isotopes, will fall first. So they start falling in the bottom of the slope, and then as you go high and high, your isotopic composition of your water goes on depleting. And this is very, very important in identifying the recharge edges of springs. So because at a higher altitude, the rainfall is depleted, whereas at the lower altitudes, the rainfall is enriched, I will say, as compared to the higher altitude. So we can find out at a certain location from where then we can find out the altitude effect, that how much is the depletion rate on a particular slope. Using that, we can identify approximate elevation from where the recharge might have taken place. After identifying that, we can go for our rejuvenation or maybe some actions for management of that area, so that we retain the more water in that area for a longer time and can recharge the springs. So altitude effect, if you see, it is observed from 1 to 4 per mil per 100 meter, while it varies from 0.15 to 0.6 per 100 meters for O18. So the normal rates are this, but for our studies, we normally find out the altitude effect at each and every slope where we have to go for our investigation. This is a general depletion rate. So if you see the depletion rate in this particular graph, this is just to give an impression how the isotopic variation takes place. If you come from Gomukh to Haldwar, you can see gradually the isotopic composition is becoming enriched as compared to the Gomukh due to this altitude effect, as well as this is mostly due to the altitude effect. Then if you see, then there is a latitude effect. Again, you can see at the polar and equatorial areas. In the equatorial areas, the moisture which will evaporate will have more fractionation rather than the polar area, because it is temperature dependent. So at a lower temperature, there is a less fractionation, and the depletion rate, if you see, is 0.65 per mil per latitude in continental areas for oxygen, and 0.2 per latitude in colder regions. So then seasonal variations also have the impact on isotopic composition of the precipitation, and I'll explain it more with the I think okay. Here you can see in the northern hemisphere, the data has been collected at different latitudes and different seasons. If you see in Midway, which is just on the polar, there is very little. You can see the top one. There is very little variation of isotopic condition throughout the year. But if you see here, vineyard, there is a lot of variation during the season. Okay. Then when the recharge takes place, how these variations are normally, you can say, subsumed. You can see if it is a 2 meter depth in clay subsurface, this seasonal variations die out. In sandy soils, in unsaturated zone, within 10 meters, it goes down. Then in 50 meters in fractured rocks, this fractionation you can see in rocks and tills up to 50 meters. And if the crystalline rocks which are dominated by fractures, this variation can be seen up to 100 meters. So in the most of the alluvial plains where we work, isotopic seasonal variations can be seen only within 10 meters depending on the soil. Then there is another effect which is the amount effect. So this is normally an effect which is very effective in the arid areas, because when the raindrop falls from the even during the very low intensity rainfall, and during in the arid areas there is a evaporation from the drop itself. So there is a drop from the surface of the drop. This evaporation takes place, and which causes this fractionation. And we can see the in this diagram you can see, or the picture you can see how this is effective. And there is a rainfall of 2 millimeters per year per hour of 2 hours of rainfall. You can see here the isotopic composition is enriched, and when there is a heavy rainfall, this goes down. So isotopic composition is depleted. But this is mostly in arid areas, but in humid areas there is not much impact of this amount. You can see at Gomukh, as the rainfall increases, isotopic composition decreases. Gangotri, rainfall increases, isotopic composition decreases. Similarly, Dabrani, Devriyag in Himalayas. So these have been some of the studies which have been done in NIH. So this is the isotopic variation, hydrological cycle of isotopic variation. You can see. So I told you the vapor, the water which is there in the sea is having 0 isotopic composition, which is the standard which we take. Then there is evaporation, and as we go away from here, the isotopic composition of the moisture vapor goes on changing. Then this is a very important concept of global meteoric water line. That means on the globe, if you take the precipitation at any place, it will always fall on this straight line. So this straight line is known as the global meteoric water line. And in the warmer regions, the samples, the isotopic composition of hydrogen and oxygen, if you plot, will fall on the upper part of this, and in colder region, it will fall on the lower part of this. Because I told you in the colder regions, there is only the lighter moisture, which is because heavier moisture has already been fallen as rainfall in the warmer region. So this is then this is the global meteoric water line, which is a straight line, and which is you can see this is nothing but del D is equal to a coefficient A into del O18 plus D. This is an intercept. So this is the equation of a straight line, and this straight line was first defined by Descriand as del D is equal to 8 times del O18 plus 10 per mil. But there are some variation with the local climatic conditions, which is the equation for northern hemisphere has been, because more and more data is coming now. Earlier equation was based on very limited data, but now large amount of data has come, and which has now this has been slightly modified as del D is equal to 8.17 del O18 plus 11.27 per mil for northern hemisphere. But the standard global meteoric water lines which are taken are as for northern hemisphere, it is the intercept is 10, and for southern hemisphere it is 22. So if after rainfall any process happens on that, because I told you precipitation, if it is there, it has to fall on this particular line. This is a global meteoric water line. If there is any evaporation, any mixing, or any other process which is acting on that water can be identified by these lines. Because in the ocean, as in the coastal area, let us start with, in the ocean area, I told you the ocean water is 0, and the normal rainfall which falls in the coastal area has an isotopic composition of -4 for oxygen and -22 of hydrogen. So this is the general average isotopic composition of the rainfall which happens in the coastal area. So if there is any mixing of these two, that samples will lie on this line. So any sample which is lying in the coastal area on this line clearly indicates that there is a mixing of the ocean water with the rainwater or rainwater induced groundwater recharge or rainwater surface water. Then in the estuarine areas, this is the estuarine mixing. Then you have a groundwater line which lies between the evaporation line and the ocean this estuarine mixing line. And this is because whenever there is evaporation, it deviates from your global meteoric water lines, and it always lies in the lower part of this, and the water or the moisture which is escaping has the isotopic composition which is above this global meteoric water line. So this is a global this Indian meteoric water line. This has been developed at NIH using a large number of samples. Now you can see Indian meteoric water line is very, very close to the global meteoric water line. It is having 8.17, it is 8.11, and it is 11.27, it is 11.33. So our meteoric water line, which has been developed here in NIH, is very, very close to the global meteoric water, and it has to be, because this is part of the northern hemisphere. Then if you see this particular graph, you can see the samples which have been taken from Patna, Bangalore, Belgaum, Kakinada, Sagar, Jabalpur, and Jammu. I told you about the continental effect. As the moisture moves away from your coastal areas, Kakinada towards Jammu, you can see there is a distinct variation in the isotopic composition, but all the samples are lying on the one line. Then in the beginning itself, or I told you that evapotranspiration does not have any fractionation. So water, here you can see this is the Belgaum area, which is having a dense forest, densely forested area, and most local moisture which is there is having this isotopic composition. And rest of the moisture you can see, which is coming from the Bay of Bengal or Arabian Sea, is showing a distinct fractionation as it moves from the coastal area towards the Jammu and far away from the source. So these are the isotopic composition at different part of the country. You can see the moisture which is coming from the Mediterranean has basically the d-axis, which is not 22, it is between 14 to 22. We have observed in Nepal, we have observed in Sikkim, we have observed in Kashmir, the most of the snowfall, which is because the snowfall normally falls in the summer, this winter season, and winter season there is no moisture from the your Bay of Bengal or Arabian Sea. This is only the western disturbances which bring the water. So we have seen this values of d-axis in most of the water which are there in the Himalayas, even Nepal, in Sikkim, and so on and so forth. So if you see the coastal area, the moisture is -1 plus -1. This is for the eastern coast. For west coast, this is east coast. The approximate or the general isotopic composition is -+/-2 per mil, and dx is 10 ± 5. So this is the different parts we have of the country. We have different isotopic composition. Then I told you one thing about the climatic effect. Climatic effect is not the direct effect, as I told you, but it gives a very good indication about the climate which might have existed at a particular time. So temperate climates have experienced significant change in temperature since the late Pleistocene time, and such climate change are manifested by a shift in the stable isotope component content of precipitation and in deuterium axis. This I will explain with the help of this figure. You can see here there are two groundwaters in the two aquifers. You can see here the isotopic composition is entirely different from the deeper aquifer water, which is old water, and the modern water of this groundwater is matches with the precipitation which takes place in the modern times, that is in recent years. But it clearly shows that the water which is down there in the deeper aquifer is the water which was recharged at a time when the climate was cooler. Because you see, as I told you, it is temperature dependent. On the cold climate, we have the depleted signatures of the isotopes, whereas in the arid and higher temperature, we have the enriched signature of the water. Now I will show you quickly some of the case studies. No, okay, I will just first tell the applications. We can use isotopes for soil moisture variation and its movement, origin or source of groundwater and its age, recharge sources and zones of aquifer, groundwater recharge flow with direction, base flow to surface water bodies, whether the base flow is coming to the river or not, because nowadays there is a lot of concern the base flow is reducing, so we can find out how much base flow is coming into the rivers. Then in groundwater, again, salinization of groundwater in inland and coastal aquifers, and sources of pollution, effectiveness of artificial recharge, how far the recharge has gone. Then groundwater and surface water interaction, aquifer interaction, investigations for spring rejuvenation, identifying pollution-free water, because you know the industrialization has started only during the last 200 or so years. So any water which is older than that may be protected from they may not have been polluted by the industrialization just taken place from 18s or 1850s. So any water which is older than that may be pollution-free water. Then this is the thing which we have done in Nainital. You can see in the figure here. This is again surface water groundwater interaction here. How much water is the lake water balance we did with isotope? How much water is from direct precipitation? How much is vapor transpiration? How much is the outflow? How much is the water coming from the spring as a subsurface discharge into the lake that we have done using this isotopes. Apart from that, you can find out the suspended and bed sediment transport, discharge of mountainous rivers, seepage and leakage from water bodies, snow melt contribution. This is a very, very important aspect in the rivers. Snow-fed rivers, we can find out how much water is coming from the snow melt, how much is the groundwater composition contribution, and how much is the direct rainfall contribution or the surface runoff contribution there. This is another this surface water groundwater interaction we can do. Okay, again, this is a study which we did in Delhi area to find out whether there is an interaction of river water Yamuna with the groundwater, because a lot of tube wells have. I will come to that case study a little bit later. Then we have done this sedimentation study in lakes, that is number of lakes. This is again for environmental studies, global and regional climate change. We can use isotopes, origin and evolution of rain-bearing vapor. Here in this figure, I want to just show, as soon as the moisture arrives, the isotopic composition of the atmospheric moisture decreases. As you can see, as there is a decrease in isotopic composition of moisture, then there is a start of monsoon. And as soon as it withdraws, if you go on taking the samples, you can find out when the moisture from Arabian Sea or the west of this Bay of Bengal has reached. You start sampling the air moisture. You start collecting the air moisture and try to analyze it. If it is suddenly starts depleting, that means the water from Arabian Sea has come. Otherwise, this is all the local moisture. This is the local moisture generated from the local areas, and the moisture which is very depleted is traveling from the Bay of Bengal. So this way we can find out the time of onset of monsoon and the withdrawal of monsoon. So, so quickly I will show you some of the case studies. So this is a study which we are continuing from last 20 years in the Gangotri Glacier. We have our gauging site, we have our hut, this insulated hut at Gangotri Glacier. We have meteorological observatory, and there was a concept that when there is no contribution of rainfall on recharge, this discharge of the river, whenever there is a rainfall, the discharge decreases rather than increases. Then it was investigated and it was found that there is a contribution of, because if you see the isotopic composition of before rain, the river was minus 14.8. After rain, it was minus 20.54. So rainfall on rain has the isotopic contribution of minus 30/26. So rainfall contribution is 38%. Based on the isotopic composition, the content or the fraction of different sources has been computed at different places. This is another study which we did for Yamuna, which I was showing you earlier on the Yamuna river map I was showing. There are a number of tube wells which have been constructed along this river, and there are some differences of opinion between there were, I don't know now what is there, that these rivers, these wells are pumping water from the river. Then we carried out the isotopic investigations by constructing piezometers all across the rivers, and we sampled these piezometers for isotopic composition, and we saw that, you see, here is the depleted, that means this area has, because the river Yamuna is coming from higher altitudes, so it has the water which is depleted than the rainfall which is taking place in the this Delhi area or the UP area in around Yamuna. So we found that in some areas there was some depleted area, but this, when we analyzed this further, we found that this is all only during the floods. The water is getting recharged in the floodplain. So this is the floodplain area, and water is getting recharged into it from the river Yamuna, and away there is no interaction with the groundwater. So if we took the samples on different dates at different distances, and we found out when there is a depleted peak which has come in Yamuna is traced in the different piezometers, and we could find out that from this point here to this point it took around 40 days, and the distance between this is 80 meters. So that means the travel time within the floodplain is 2 meters per day within in this very close to the active river. And if you go away from the active river, the velocity of water in the floodplain was found to be 1 meter per day. So if the velocity of water is 1 meter per day and the floodplain is 1,000 meters wide, so you can see that only up to maybe 400 meters or 350 or 400 meters the water will move. So there is if the wells are at a distance of maybe 800 or 900 meters away from the active channel, that means the water will not move into those wells from the river. Between piezometer number 2 and 3, number of days between different peaks and this of isotopes in river water within the piezometer, some signatures have been traced. You can see here there is a peak coming, here there is a peak coming. The distance is around 220 meters, and it took 224 days for this peak has to travel from this to this. So this gives the groundwater velocity. Then similarly, we can use the groundwater age. If you know the age in one well and an age in the other well, you can find out from which well side the water is traveling. So we can find out the velocity. Here the age is 2500, here 3000. So the distance we know between two wells, we can find out the groundwater velocity within the aquifer. So, and also the groundwater flow direction, because the younger water will be closer to the recharge zones and the older water will be away from the recharge zone. So we can find out where, in which direction the recharge zones are located. This is a case study which has been done by NGRI in the Naveli lignite area. You can see here, this is the isochrones. You can see the age contours 50 years, 500 years, 1000 years, 2005, 25,000 years. So it is showing clearly that the recharge area is in this area, and groundwater into the mines, these are the coal lignite mines, is coming from this direction. Then similarly for sedimentation studies, because cesium was again produced, you can see in different peaks we have this marker horizons. 1957, 58, 63, 64, 86, 87. And if we take the core of the sediment from the lake, we can find out which we take a core, we slice it at 2 centimeter thickness and find out the cesium content in that, and that gives, you can see here that cesium is increasing here. This is one peak, another peak, one peak, one peak. So how much sediment has deposited from today to till that peak, can find out the sedimentation rate in reservoirs. So by this we have done a lot of studies in Dal Lagin, Mansa, Bhimtal, Nakuchia Tal, Sattal, Nainital lakes, and these are the average sedimentation rates which has been found using these techniques. There are many case studies and which are there, but the time I have already overspent the time, so I will like to stop it here. And we have found out the age of Nainital Lake as around 2300 years. So if the current rate of sedimentation continues, so it will be, because the Himalayan lakes are formed and then they disappear due to sedimentation. Again, they are formed due to tectonic activities. So the present sedimentation rate which is there in Nainital Lake, the lake will survive only up to for 2300 years, and this Nakuchia Tal may be 3000 years, and you have different lakes which will survive for different years. So thank you very much. We have hundreds of case stories to discuss, but time is short, so I will stop. Thank you.
Before we request our director to give his remark on the excellent presentation given by Dr. Sudhir Kumar, if there are some queries from the participants and audience, they can put forth, and I think I'll request Dr. Sudhir Kumar few queries, and we can share his mail ID. If you have some detailed queries, you can contact him. And
I have already shared my in the presentation first slide. I have given my.
Fine, sir. It's being recorded. We'll put it on the website so people can see it. Yeah. That is okay. If there are any queries, people can take that.
May I, sir? I have a small query from that presentation.
Yes, you can have.
Sir, in one of slide you have shown in near Delhi, near Yamuna, that transmission speed or velocity of groundwater is something 2 meter per day or 1 meter per day if you move far. So in that calculation, I think it is interpreted that hardly 400 meter or 300 meter in a year means from rainy season to dry season, I guess. So that much only will be influenced.
Yes, if there is no flooding, because most of the recharge, so that is the major actually controversy.
Sir.
If there is no flooding, then only water will travel up to this distance. But most of the time there is flooding, so that the water which the Delhi Jal Board is expecting from the floodplain is mostly, it is the flood recharge, that is the bank storage which has developed due to the flooding, not it is directly connected to the river water. So lean season, whatsoever they are pumping is the water which is recharged during the flood season. So that is the point.
Oh, I think clear, sir. Okay, thank you.
Anyone else?
Sir, I would like to ask one question.
Yeah, please.
Sir, in our soil and water conservation works, we execute a lot of these conservation measures, like the water conservation techniques, like recharge speeds and trenching etc. So what do we want to know, that how much water has been recharged from these particular structures? Naturally, how much has been recharged? And particularly hilly Himalayan water sets with a small area of 500 hectare. Can it be? Ji, sir. Yes.
I have done a similar, what you are asking, we have done a study in Aravalli Hills in Rajasthan.
Right, sir.
Whether this water conservation measures which we are taking is effective or not, whether
Yes.
it is really recharging the groundwater or not.
Yes.
Very close to the structure, we have found few wells getting recharged.
Okay.
So that is already, we have already seen it. It all, because mostly the conservation measure, what we are doing, you are making check dams, you are making some small structure. So if in the well we have checked whether the water, because what you do, you stop the water from flowing, so it gets evaporated. Okay, once you store the water in the structure, it gets evaporated. So evaporated signature if are coming in the well, that means your structure is recharging into the well. So that type of work we have done. We have done this type of study in Maharashtra also, where we try to see whether the artificial recharge measures which have been taken, how far they are effective. So if you see the water composition which you are recharging, how far it is going. So you can, if you have some wells nearby, you can always collect the water sample and check it, whether that water traces are there or not.
Yes, sir. Actually, it's not well, because in the Himalayan water study, those perennial streams. I want to check at the outlet of the perennial stream. If there is improvement in water yield, then how much has been recharged from the trenches or whatever techniques that we apply for recharging. So it's like a very short-term gain kind of thing, seasonal values.
So that we have, very frankly, that we have not done.
Okay,
but
sir.
if possible, we can collaborate with you and try in 1 or 2 cases.
Okay, okay, sir. Thank you, sir.
Yeah, I have one question, Sudhir Kumar ji.
Answer.
Normally we presume that the water harvesting structure, either a small scale to the bigger scale, only contributing to the groundwater recharge. Otherwise, in the catchment area, intensive in situ moisture conservation practices like bunding and terracing and other agronomic measures, and also the small scale, the mechanical measures also they take place. There, I feel that their contribution to the recharging, particularly the groundwater, and also the rejuvenating the stream, also much more as compared to not only our water harvesting structure.
Yeah.
That is my first question. The second question is that normally we observe that the recharge from the water resources, where either in the tanks or whatever the thing, in the lower downstream side.
Yeah.
Depending upon the geographical condition and geology of the land terrain, even some cases, even in the upstream side also, there is a chance of recharges.
Upstream, I don't think there will be any impact of it, because by gravity water will move down, it will not go up. So I have a collaboration with IMI in Nepal. So there also we try to find out the impact of structures which you are talking about. They made some tank to store the water and see whether the tank water is recharging into the groundwater or not. And we could find only to some extent there was recharge wherever there is a fracture. Otherwise, groundwater recharge in a hilly area is very, very tricky issue, because it all depends on the fracture system present there. And on the purpose of mostly the groundwater storage tanks which we are producing, not the groundwater recharge, but to collect the water and use it there itself at the same time. So that type of study we have not tried in Himalayas, but again I am saying that if our institute Tejas says, then we can think of something and find out whether there is any impact of these small structures on recharge. We can have some small piezometers installed around 1 or 2 structures and then see what is the impact it is giving.
So
that is the purpose, actually, to invite people and use this technology for unanswered questions.
Yeah.
So that way, I think today's webinar will be very, very, very useful for all of us. दुबे साहब कुछ कह रहे थे.
हाँ, नमस्कार सुधीर कुमार जी, नमस्कार.
हाँ, नमस्कार.
मैं डॉक्टर दुबे हूँ और इस लॉट में से रिटायर्ड आदमी हूँ. और मैं आपको धन्यवाद देना चाहता हूँ कि पूरा मेरा बचपन जो है वो इसी डर में बिताया गया कि इधर रेडियो एक्टिव मटेरियल है, इधर मत आना, इधर आइसोटोपिक लैब है, इधर मत आना, मर जाओगे, ये हो जाएगा, वो हो जाएगा. You have put such a wonderful way, such a difficult subject, इतने आसानी से समझाया, इसके लिए मैं आपको दिल से धन्यवाद देना चाहता हूँ. और साइंटिफिक क्वेश्चन नहीं होगा, लेकिन मैं आपको ये बताना चाहता हूँ कि हमारे पास आपका भी आइसोटोप है. जो श्री माली जी हैं, इनके एक क्लासमेट हैं डॉक्टर खन्ना।
हाँ हाँ,
वो देखने में बिल्कुल आप जैसे लगते हैं। मैं ये सेमिनार सिर्फ
Yes,
इसलिए
yes.
अटेंड किया हूँ।
Yes, yes, yes.
आइसोटोप पे क्या बोलेगा?
Resembling another
Resemblance
isotope.
is
Yeah.
98%.
Mhm.
So I joined here only to see how Khanna is going to speak on radioisotopes. Because he was my colleague also. He is working as a principal scientist in IARI, Water Technology Center. And so once again, congratulations for you for such a wonderful talk. Thank you very much. You have made my day.
Sir, can I ask a question, sir?
Yes, yes, yes.
हाँ,
Goel ji,
मैं-
आप तो Yeah,
Sudhir ji, this is I am R.K. Goel from Kajri.
I know, sir.
पहले से आपसे कई बार मेरा मिलना हुआ है।
हाँ,
छोटा सा
हाँ।
मेरा क्वेश्चन ये है कि राजस्थान के अंदर MJSA की स्कीम चल रही है। MJSA मीन्स मुख्यमंत्री जल स्वावलंबन अभियान, और इसके तहत बहुत सारे स्ट्रक्चर्स बनवाए गए सरफेस के ऊपर। आप उसको कह सकते हैं फार्म पॉन्ड कह सकते हैं, जो भी कह सकते हैं, स्ट्रक्चर्स बने हुए हैं। और जाहिर सी बात है बारिश में पानी आता है उनके अंदर, वो भी सही है, मतलब ये है। लेकिन मेरा एक ऑब्जर्वेशन ये है कि रिचार्ज की प्रोसेस बहुत स्लो होती है यहाँ पर, और उससे पहले 80 to 90% पानी ऑपरेट हो जाता है बिना काम में लिए हुए। ये एक मेरा अनुभव है इस चीज के बारे में। और मुझे एक ऐसी कमेटी में डाला गया है, मेरे से पूछा गया है कि इन स्ट्रक्चर से कितना हो रहा है रिचार्ज।
अच्छा।
मुझे उनको जवाब देना है इस चीज का कि वास्तव में इन स्ट्रक्चर से कितना हो रहा है रिचार्ज। मैंने उनसे कहा था इस चीज के लिए कि प्राइमरीली पानी ऑपरेट हो रहा है, ये रिचार्ज इतना नहीं कर पाएगा।
किस एरिया की बात कर रहे हैं आप राजस्थान में?
जी,
Which area are you talking about in
मैं
Rajasthan?
राजस्थान के, आप चाहे जोधपुर की बात कर रहे हैं, चाहे आप जयपुर की बात कर रहे हैं, वो स्कीम तो एंटायर राजस्थान के अंदर है, और ऑपरेशन लॉसेस काफी है हमारे यहाँ भैया। तो मेरा एक स्पेसिफिक क्वेश्चन ये है कि एक तो डाउन स्ट्रीम में वेल वगैरह मिल जाएंगे हमें, वेल के लेवल से बात बनेगी नहीं हमारी, क्योंकि फार्मर्स पानी को विड्रॉ कर रहा है, तो लेवल से नापने से तो बात बनेगी नहीं हमारी। द ओनली मेथड इज टू गेट सैंपल्ड बाय यू। आइसोटोप सैंपलिंग की जो बात कर रहे हैं उससे हो सकता है। तो सर क्या आप निकाल सकते हैं इसमें कितना परसेंटेज मतलब रिचार्ज, ऐसा निकाल सकते हैं इस तरह का?
यस यस यस,
स्पेसिफिक मतलब ये। अच्छा, दूसरा सर, ये आपके सैंपलिंग का कोई चार्ज वगैरह इस तरह का हो, मतलब हम बल्क में सैंपल यहाँ से भेजना कुछ करते हैं, इस तरह का कुछ आप बता पाएंगे इस बारे में थोड़ा सा?
एनालिसिस चार्जेस तो हैं, क्योंकि हमको भी लैब मेंटेन
नहीं, मैं चार्जेस तो होने चाहिए, वो तो वी वर्क इन सिस्टम, केवल एक जानने के लिए, जैसे कभी प्रपोज करें इस चीज के लिए कि हम कुछ
चार्जेस हैं, वी कैन टॉक अबाउट दिस।
अच्छा, चलिए ठीक है। थैंक यू वेरी मच, इट वाज अ वेरी नाइस लेक्चर एंड वी रियली एंजॉय योर लेक्चर। थैंक यू।
So I think we can request now our director, Dr. Madhu, to share about the presentation and the concluding remarks.
Yeah, thank you very much, Dr. Srimali ji. Dr. Sudhir Kumar ji, today's speaker on use of application of isotopes, particularly in the hydrology related aspect. And head of the division, Dr. P.R. Ozisi ji, and Dr. R.K. Goel ji from Kajri, and Dr. S.K. Dubey ji, our ex-colleague, and head of the centers, and my scientist colleagues, and our regular officer colleagues, those who are working in the State Department. They are on the online, and also some few students who have joined this session. On behalf of UHAD, I profusely thank Dr. Sudhir Kumar ji. Yes, such a complicated topic, he has made it as simple and wonderful, and it can be understandable at any level. On behalf of Indians of Soil and Water Conservation, on behalf of all the online participants, we express Sudhir ji our dhanyavad. Thank you for sparing your valuable time.
Thank you.
And my dear friends, we know that the water, this technique definitely it can be applicable wherever the water is involved. There is not a problem, because he has made it the altitudinal variation, latitudinal variation in the different forms of water. And definitely this technology, it is having a wonderful, and also he has told that only the the instrument is the only a costliest part, otherwise the remaining part is not that much. Either analytical part or sampling part and other things. In that view, my dear friends, we are implementing so many programs on watershed scales. In that aspect, the soil is also one of the important aspects. Of course, the few of our team scientists colleagues are already they are using this isotopic technology for the assessing the soil erosion and also the carbon related thing. Particularly the related to the water I request Pierre Ojaswiji to take a lead. And also I request my scientist colleague, particularly from the engineering colleague from the regional station, to take a conceptual idea application of these isotopes, particularly assessing our intervention, the impact of hydrological impact of our intervention on watershed basis. I think it is a very time is matured now. If we are not adjusting now, I think we are not in a position to address in future also. Simultaneously, I also request my soil scientist colleagues, because the nutrient dynamic also a important process once we talk about the conservation aspect. Similarly, our forest scientists, because where they involved horticulture and other tree plantations, there the large scale, the water balancing and also the coupled with the nutrient, the recycling mechanism, that definitely this the technique is much more useful. I request all the scientists of engineer and also the soil scientists and plant science scientists and other scientists to take a note of this and come out with some of the either collaborative project or externally funded project. If possible, we can purchase, if fund provides, we can purchase one or two equipment if it is possible. As he was mentioned, it is only a too costly process. Otherwise, remaining processes remain same. Yeah, with this, I thank Pierre Ojaswiji for organizing this event. It is much more fruitful to our own scientist colleagues and also those officers who are working in the State Department at the different states. Sudhir Kumar ji, as of now, we are having nearly 26 officer trainees from different states. They are also participated and enjoyed your lecture. Yeah, thank you very much. With this, Sudhir Kumar ji, at any time, you are most welcome to Dehradun University of Soil and Water Conservation. Either in a collaborative mood or otherwise also. Dhanyavad, thank you very much. Namaskar.
I request one of our fellow colleague, Dr. Patra, to propose vote of thanks on behalf of Division of Hydrology and Engineering.
So thank you, sir. Thank you, Dr. Sudhir Kumar, sir, for your very informative and elaborate talk on basics and applications of isotope hydrology. I think this is the science that is most applicable for soil and water conservation. And we are a soil and water conservation institute. I think we should take maximum benefit from your talk. And I also thank our director for encouraging such kind of talks under the Azadi Amrit Mahotsav program, and also for his talk on encouraging our scientists for taking up similar projects. And I also would like to thank Dr. Pierre Ojaswiji, sir, Head of Hydrology and Engineering Division, for taking keen interest in arranging this particular talk. I also thank Engineer S.S. Rimali, sir, and AKMU section for arranging this wonderful platform, that is online Zoom platform, for smoothly conducting this particular talk. I would also like to thank our all regular course trainees and all the eminent scientists from other institutes and participants from other institutes for actively participating in this seminar and also asking relevant questions. And I thank you all. So thanks, sir.
Thank you, sir. Thank you. Thank you. John.